This episode will cover permutations of objects. As you can read from the definition, a permutation of a set of objects is an arrangement where we take order into account when considering whether two orders are the same or not. Thus, changing the order results in a new permutation that we add to the total number of permutations. We will have a look in future episodes where, if we have the same set of objects but in a different order, we consider this not to be unique. Episode 1 will focus on permutations of the whole set of objects, as well as a subset of objects. So, one might say arrange 3 objects out of 5 rather than all the objects. We will then look at what happens when we have repeated objects within the original set. Episode 2 will use the concepts from the first video in order to create the choose formula, and then look at problems where order is not important, finding the number of combinations. Finally, we will look at different types of questions and how to break down problems, as, in my experience, this is a topic that is mastered by looking at the questions as well as forming a deep understanding. The order here replicates the order I would structure for my classes, and looks at how and why we use factorials, so you will develop a deep understanding and not just tricks to solve questions. Firstly, I always set my classes a question similar to this, as, if all else fails, they can list out the combinations and then try to find a more efficient method. My hint though, and this is where the first concept comes from, is that this can be solved by drawing a tree diagram. In this tree diagram, each column will relate to one of the slots that a student would fit into. I will use this idea of slots throughout the video. For the first slot, there are 4 options and thus 4 branches on our tree diagram. The next slot now has 3 options to choose from, as one person will already be in the first slot. Thus, each of the 4 branches from the first column now has 3 branches coming off them. There will therefore be 4 times 3 branches in total. Now, we are running out of room, so I need you to use your imagination, but each of these 4 times 3 branches will have 2 branches coming off them for the third slot, thus giving us 4 times 3 times 2 branches in total. Finally, the final slot will only have one option, so we will have 4 times 3 times 2 times 1 branches in total. This corresponds to the total number of permutations, as every single permutation is included in this tree diagram. I have not evaluated the calculation, as we can see it forms a pattern starting with the number of objects and multiplying by consecutive decreasing numbers until we get to 1. In short, this is known as 4 factorial and denoted by this notation. In the future, I won't continue to draw the tree diagrams out, but we should now understand why we use factorials in this type of problem. Note that I could change the problem slightly so that factorials wouldn't be the solution. If I only have 2 slots, then I will only have 2 columns in the tree diagram, and thus only 4 times 3 lots of permutations. We shouldn't use factorials blindly because they are linked to permutations, but think about how many slots there are and thus how many branches in total in the corresponding tree diagram. This next problem also doesn't involve factorials, as we are not using up members of the set, and partway through we even change the set of objects we are choosing from. In this example, the first column of the tree diagram will have 26 branches corresponding to the letters of the alphabet. Similarly, the second, third and fourth columns will each have 26 branches, and the final 3 columns will give us 10 branches for each path they come off. Our next problem is similar to the first, and we can use factorials as we are arranging 10 people in a row. Thus we will use up 1 person each time we fill a slot, and the number of branches we are adding to each path on the tree diagram will decrease by 1 each time. Therefore, the total number of permutations is 10 factorial. This type of question, though, we can expand upon. Next, there are some restrictions, with the boys having to sit together. In order to solve a problem like this, I believe it is important to think about one specific situation and then expand from there, as we will see we will be able to duplicate these situations. So if we find a number of permutations of 1, we can multiply it by how many situations there are. Here, I have fixed the boys at the left-hand side, and the girls will fit the remaining 7 places. Boy 1, 2 and 3 will be fixed in this position, and there are 7 factorial different ways the girls can fit alongside them. Next, I can switch the boys around, but keeping them on the left-hand side. And again, there will be 7 factorial ways the girls can fit with them. I can do this again, and it will still be 7 factorial, and so on, until I get 6 different lots of 7 factorial. Let's now think about where this 6 comes from. It comes from the number of ways I can arrange the boys in these 3 places, which is 3 factorial, by thinking about the tree diagram associated. Now I have found the number of permutations with the boys sat in the left-hand side, I can move them across by 1, and see this will also give 3 factorial times 7 factorial lots of permutations, as the girls will still fit around 1 arrangement of boys in 7 factorial ways, because I still have 7 slots to fill with 7 girls. I can repeat this process and count that there are 8 different places I can put the 3 boys in by sliding them from left to right by 1 each time. This gives me a total of 3 factorial times 7 factorial times 8 number of permutations, or 241,920 permutations. Now let's look at the next follow-up to this same question. There are 2 ways to think about this problem, such that we can find a number of permutations where all the boys don't sit together. Firstly, I can think about the number of permutations where only 2 boys sit together, then the number of permutations where no boys sit together, and then add them together to find the total. Or, I can think about the total number of permutations and subtract the number of permutations where they all do sit together. Not only have I already found this in the second point, but in the first, there are more than one type of permutation to think about, so double the amount of working. Therefore, this is the total number of permutations. Note I can simplify this slightly, as 7 factorial times 8 is the same as 8 factorial. I mention this as a manipulation of factorials is an important part of IBDP mathematics. Furthermore, this concept where we think about the total minus the number of permutations we don't want can be translated across to different topics. You may have come across questions such as finding area, where instead of adding up area of compound shapes, we can find the total area and take away the area we don't want. Similarly, in probability, the concept comes up as well. Instead of finding the different types of combination, adding their probabilities together, we can think of the total probability of 1 and subtract away the combinations we don't want. My final type of question involves arranging a set of letters, as this will introduce repeating letters. Here we can see there are 6 slots, so the corresponding tree diagram would have 6 factorial lots of paths. However, what does it mean if there are 2 letter E's? Well, if I number these letters, then you can see the original word would appear twice, one with the first E coming first, and one with the second E coming first. If we consider another permutation, there will be a repeat also, and another. I've arranged the permutations into 2 groups, as we can see that the number of permutations formed by 6 factorial will have each permutation repeated. Therefore, we can see the total number of unique permutations would be 6 factorial over 2. At this point with my classes, I always introduce a word with 3 of a letter, as, without thinking, one just presumes that we would divide by 3. However, think about why we divide by 2, and how many repeats of the same permutation there would be. It is the number of ways we can arrange the repeating letters, which would be 2 factorial, so we should write it as such. And the number of ways we can arrange 3 of the same letter would be 3 factorial. So there would be 3 factorial groups, each with unique permutations in it. so the answer would be 7 factorial over 3 factorial. Finally, what about if there is more than one repeating letter? Again, we should think about how many ways we can arrange the 3 P's and the 2 O's to get the same permutation. This is similar to arranging the boys and girls in a line, as I can fix the 2 O's and then arrange the 3 P's in 3 factorial different ways around them. Then I could switch the O's around and do the same thing with the P's. There are 2 factorial different ways to arrange the O's, so 3 factorial times 2 factorial different ways to arrange them all. Therefore, the final answer would be 12 factorial divided by 3 factorial times 2 factorial, with the 12 factorial relating to the number of slots. The main points of this video is that, firstly, factorials are associated with permutations through tree diagrams. Notice how I don't need to refer to any p function on the calculator. Secondly, if we want to break down a problem, we should think about slots, and then focus on one situation and find a number of permutations before we find the total number of situations. I hope this video has been helpful and given you a deeper understanding of permutations before we move on to combinations.